Okay, Dan, it's all yours.
Have you muted him?
All right, are we up?
Yep.
Very
We
good.
are up.
Thank you for the opportunity to present to your group there in Australia. I hope many of you had the chance to go through the class on the impact of ventilation on room fires and fire patterns. We're going to just do a brief introduction of who UL Fire Safety Research Institute is. We'll do a review of the class that you took, just hitting the highlights, and then we'll pause for some questions that you'll feed through Mark in the chat. And then we'll talk about some other fire investigation research that's going on at FSRI, some of it addressing firefighter investigator exposures to cancer-causing agents, and some of it on continuing on the impact of ventilation, but now looking at it with buildings with real windows and HVAC systems operating. So I'm sure many of you have heard of Underwriters Laboratory worldwide. Underwriters Laboratory, or UL, has 15,000 employees, and that's the UL for-profit side. So they do all the testing, inspections, certifications, things of that nature. I work for the not-for-profit side in the research group, and there's about 130 of us total. We get most of our funding from the for-profit side. The difference is you basically can't get any data from the UL for-profit side. The reason being is that the data is owned by their clients. So if somebody submits their car or their battery pack or their fire hose or whatever it is for testing for a UL listing, whatever data is generated from that is proprietary between UL and the client, because the client owns the data. Everything that we do on the not-for-profit side, the data is in public domain. We want to share everything we do, and we work hard through training, or as you'll see, data repositories that we're putting up to try to share that information. So we originally, when they started the fire group in the non-for-profit, it was called the Firefighter Safety Research Institute. And last year we changed the name. While we still have a mission to serve the firefighters and help them to be more effective and do their jobs safer, we had been doing work to support fire investigators as well. And they said, well, let's just change the name and call it the Fire Safety Research Institute to be more inclusive of what we're really doing. And so this is just sort of an idea of the different areas, all the areas that we're hitting with regard to fire, whether it's prevention or suppression or active passive resistance, detection, alarm. And of course, all of this engages investigation, because whether it's a materials issue or a systems issue, that could all become part of a fire investigation, trying to understand the origin and cause, or maybe just trying to understand why the fire behaved the way that it did. So historically, old school fire investigators, they had some ideas that if a pour pattern was found on the floor, it was likely that, start thinking about flammable liquids. And if flammable liquids are involved, start thinking about arson. If you had low burning, maybe the use of flammable liquids was involved. Heavy black smoke coming off of the fire when the firefighters arrived. Collapsed springs in furniture and mattresses. Crazed glass. You may know of some others. And then last but not least, if there was a remote and distinct fire origin, one or more remote and distinct fire origin areas, or what looked like fire origin areas, that definitely equaled arson. Well, as it turns out, some of these things at one time may have been true, or may have supported the evidence that they collected. But then as contents changed, as we'll see in this upcoming video, Perhaps the furniture now effectively came prepackaged with liquid fuel, if you will, or fuel that would turn into liquid. Today's environment, we have larger homes, more open spaces. It changes the ventilation profile of the house and where fires can burn and where they can't burn. With the open spaces, that comes with lightweight construction typically, which means that we can span longer distances instead of being limited to 3 to 4 meters or so with solid joists. Now we can span areas that might be 6 meters or 8 meters or more. But what comes with that typically is a void space for the joist. Then we have new technologies, batteries, that types of batteries and battery operated equipment that just weren't in people's homes 10 years ago. All of these things are leading up to the potential for faster fire propagation. And with the heavy fuel loads, also the realization of event limited fire. So here you can see that we've got a older sofa that is cotton upholstery with steel springs in the cushions because cotton doesn't hold its shape very well. And then we have another sofa made out of synthetic materials, polyurethane foam cushions, polyester batting. And as you can see, there's a little bit of a difference in their fire behavior. Notice that with the synthetic sofa, we have low burning, we have melting, we have dripping, and we're going to end up with something that looks like a pour pattern under the sofa because the polyurethane foam melts and drips and burns. That's not the case with the older furnishings. The more natural furnishings made out of wood and cotton and wool do not melt and drip and burn. So some of these ideas that fire investigators were developing in the 1940s and the 1950s were correct. However, when that information got translated to fire investigators in the 70s, in the 80s, when this new furnishings really took hold, they started coming into our homes earlier than that. But when they really became popular, the fire investigators were basically didn't know why they were looking for a pattern or looking for this. And they just kind of accepted a list of rules that now they were potentially applying in a bad way or misapplying. So as we can see, that cotton sofa is taking a long time to burn. And in fact, it's going to take about a We're good. Said the host muted me.
Yeah, I think I'm, yeah, carry on.
We're good. All right. So here we have the heat release rate curves of the synthetic sofa in blue and the cotton sofa in orange. We could see the synthetic sofa hit a peak of almost 5,000 kilowatts in terms of heat release rate, or about 5 megawatts. And that happened within about 3 minutes of ignition with an open flame. The cotton sofa, on the other hand, never got above 300 kilowatts, and it took more than an hour to burn. So very different fire behavior. Then again, here's an item that no one had in their home 10 years ago. So basically, we have a piece of a lot of people have hoverboards, scooters, e-bikes, things like that, that Many times when they're charging a damaged battery, or they've got a charger that is not appropriate for the battery that they are charging, and it causes them to go into thermal runaway, which then, as you can see there, could cause a fire. And then, the fancy feature there for fire investigators is not only does it cause a fire, but it starts shooting flaming globules of molten material around the room to potentially create other areas of things that may look like other areas of origin, multiple areas of origin. So one of the reasons, the key reason that this particular research was supported by NIJ, was it had been shown in the United States anyway that there was a lot of confusion over a pre-flashover fire pattern and a post-flashover fire pattern, or a ventilation impacted fire pattern. And the way this was demonstrated, the way this confusion was demonstrated was there were some trainers, many of them with ATF, that set up rooms that were about 3.6 meters on a side. They had a door and they had a window. They burnt the rooms post flashover, and then they had students that were coming in for a training class. Some of them were certified fire investigators, and some were not. But they asked them to define which quadrant of the room was the area of origin. And the majority of people could not do that successfully. And in fact, most of them decided that there were multiple origins, which then would bring them to the conclusion that it was arson. And in fact, what they were looking at was a pre-flashover pattern remote from a vent, and then the post-flashover damage closer to the vent. And they were unable to discern that. So we set up a series of experiments in 2 different types of homes to look at just changing the ventilation and nothing else, to look at how that impacted the fire damage and the resulting patterns. So our objectives were to look at the repeatability of the fire damage, demonstrate how changes in ventilation change the fire damage and the pattern, and then of course share all the results. As I mentioned earlier, this was supported by the U.S. Department of Justice. The National Institute of Justice is a subsection of DOJ. When we do our large scale tests like this, we want to make sure that the results are useful to people. So we tend to collect a technical panel to advise us on the experiments. And we want to have people that are in the field doing investigations, folks from the public sector, folks from the private sector, as well as academics that may be involved in research. One of the things that we noticed is, at least for the fire service, and since many fire investigators come from the fire service in the US, they had this idea of the ideal fuel controlled fire model: ignition, growth, fully developed, and decay. They weren't really aware of a ventilation controlled model where the fire would grow. Decay of the fire would begin within the structure as the oxygen was depleted. And then as ventilation to the structure changes, the fire could react violently in some cases and become fully developed. So here's just one example from the class that we were looking at. And in this case, we've got a fire developing in a living room. We have an open door. We're going to allow the fire to go to a flashover, and then we're going to observe it for some period of time post flashover. And what we'll notice is that the area of burning moves. It moves from the area of origin to a location closer to the open door. So we're seeing the fire go to flashover now. We've got a neutral plane set up at the open door where we've got fresh air going in low to continue to supply the fire with oxygen. However, the oxygen is not penetrating very deep into the living room anymore. So the original place against the far wall in that living room where the fire started has now stopped burning. And that in effect is preserving the fire pattern that was in that area of origin. You could see by the thermal image, second from the left and on the lower line, that the temperatures deeper in the space, deeper in the room are cooling off, while the temperatures closer to the door, as shown in second from the left upper level thermal imager, are getting hotter. And the reason is the flame front is moving closer and closer to the door. We had heavy black smoke coming out, and now you notice that the flames at the door are clearing up and are not as smoky. And the reason is the wood flooring in the foyer just inside the doorway there is now burning, along with some wood furniture holding a television just inside the doorway. And that's preventing the air from getting deep into the space. So all the burning's going on at the doorway. As the wood flooring chars over and the heat release rate from the floor dies down, you'll see that it sets up again to the point where we have convective circulation. So we have the higher temperature hot gases coming out of the door and fresh air going low into the door. And then we'll notice that the temperatures deeper in the room will start to go up again as air is able to get deeper and generate flaming combustion deeper in the space. So we'll take a look at some of the data from this particular test. And we see the temperature curves. They're giving us a profile from the ceiling all the way down to 1 foot or 0.3 meters above the floor. And we see as the hot gas layer grows there at about 75 seconds, we start to heat up starting at the ceiling, and then the hot gas layer descends until about 200 seconds or so. And then we see the rapid vertical increase in temperatures, indicating a transition of what would appear to be flashover conditions. We get above our threshold of 600 C, burning from the ceiling all the way down to the floor, indicating that we met that definition or criteria of flashover. But once we get up close to 1800 degrees F or about 1000 C, you'll see the temperature just starts to cool off. And that's as a result of running out of oxygen in that location. And during that time period of about 360 seconds to around 420 seconds, where we have that decrease in temperature, where some of the temperatures actually get below 600 C, that's that time period when we've got that clean burning at the door, where the oxygen entry into that space is being blocked. And then as we set up our neutral plane again and fresh air can go in low to the floor, you see the temperature increases once again. The pressure, which I'm showing in the graph on the right, basically shows that we have higher pressure at the ceiling and lower pressure just above the floor, which is giving us that convective circulation that we're looking for, fresh air coming in and hot gases coming out. We had oxygen sensors at 1.2 meters above the floor, basically in areas surrounding our area of origin, the sofa. And then in the graph on the right, we also had them at 0.1 meter above the floor. And as we can see that the higher position ones started to drop oxygen concentration sooner. And basically, since we're looking at flaming combustion or gas phase combustion, once we get below 15 to 13% or so, the flames go away in that area. And so we see that we've got that dip. So we don't have much in the way of flaming at 4 feet or above. Once we get to the 4-inch area, however, you see that we maintain the green line there. We maintain about 21% oxygen right at the front door, indicating we've got fresh air there available for combustion coming in the front door. And we see that it drops down almost to 15%, and that's that time when the flooring right in front of the door is burning. And then once that floor is kind of burned away, the oxygen concentration at that location goes back up. There is somewhat of a duality when we're looking at oxygen. If we have really effective burning right in front of the gas sensor, that could be shown as a zero oxygen concentration. So typically areas where it's not burning are those areas where we see it hovering around 5%, 10%, something like that. Also, just a demonstration that in the test house, when we have a closed door, that room is basically isolated from the flow path where the hot gases are moving around and being exchanged with the oxygen. But if we have an open door, that room rapidly fills with smoke. The oxygen in that room is the fresh air in that room is exchanged for hot gas. And then the oxygen in that room gets entrained by the fire and is used as part of for combustion. And so we could see the temperatures there. Peak temperatures in the open door bedroom were a little above 400 C near the ceiling and around 200 C, 0.3 meters above the floor. This is a graphic to try to show how, pardon me, try to show how the hot gases spread from the fire in the living room into the bedroom with the open door, into the kitchen, into the dining room areas, and then basically how that higher pressure caused the lower pressure fresh air to be forced out in the low pressure area by the base of the fire, then drew that fresh air with the fresh oxygen in it toward that until it could deplete the oxygen throughout the house, so that once we're post flashover, the only source of fresh air or fresh oxygen is due to the entry at the doorway, the front doorway. Everything else was closed. And that limitation of the only source of oxygen being the doorway results in the fire moving from the area of origin. The combustion zone then moves closer to the doorway and burns there for a longer period of time until the fire forces arrive, which results in a burn pattern in our area of origin, and then a very significant damage pattern closer to the door. Again, this could potentially lead people to think that there were multiple areas of origin when it's just the impact of ventilation. So we'll walk through a little scenario here where we're not going to see a video. Looking at the floor plan of this building, the crosshatched areas are areas where we have some fire damage, and the red circled areas are areas where maybe it looks like we've got an area of origin, perhaps. So one of them is in the living room, and that in fact was our area of origin. You can sort of see your V pattern. You've got a clean burn area. As you would take away the furniture, you would find deeper levels of char in the subfloor and the wood molding on the wall and things like that. But when we go into a bedroom that's adjacent to that room, let's see if this will. So this is the doorway to the bedroom, and then this is the bedroom that we're looking at. It looks like we have a fire damage pattern that's emanating from around the window and spreading into that room, which might give one some pause or give one an idea that maybe that is a second area of origin. So what you want to look for are your neutral planes at windows and doors, your line of demarcation to see where you had hot gas and fire moving out of the window versus fresh air coming in the window, which is providing protection to that surface, keeping it soot free and keeping it free from some level of fire damage. So we see that we've got air exchange and hot gas exchange, both bidirectional flow at both that bedroom window and the front door of the living room.
Hey, Dan, can I ask you a question? Did you have any furnishings on the window? So any curtains or anything that drop down?
In this particular one, we did not have any curtains. The decision by the tech panel was we wanted to control the openings, so we didn't have real windows in these. So we tended not to have curtains. So yeah, in this particular case, all we had was a window opening for that bedroom.
Yeah, okay. Because yeah, generally the curtains dropping down create what appears to be an origin, but that's why I thought that just wanted to clarify that section. Yeah,
Sure. So we did have a bed in there that had pillows and a comforter and things like that. So we had we did have the room furnished with carpeting and bedding and a dresser and some materials on the walls and things, but no curtains in this case.
Okay, just a couple of other questions. I've got a question about a pressure sensor in the room, but I think you've sort of covered that. Yeah, I'm not exactly sure. And just going back to the hoverboard, how did you make that hoverboard catch fire?
So basically, we put a cartridge heater in among the batteries and caused it to go in a thermal runaway.
Okay, excellent. That's all the questions at the moment.
So what we do is we put pressure sensors in each of the rooms at 3 different positions, near the ceiling, near the floor, and mid-height, to see we can track the circulation. So when we're looking in the bedroom, the picture on the upper left here, we see where, let's start here, I guess, actually. This is our area of origin. And so heat from the initial fire entered the bedroom. And as it's moving in the bedroom, in this lower area here, it's oxygen depleted. We had a measurement at 4 feet and a measurement at, 1.2 meters and 0.1 meter above the floor. And we're oxygen depleted here for most of the fire. We're well below 15%. So it can't really burn here. We just have thermal damage, but we don't have flaming. And then as we move across the hallway into the bedroom, we can see where the hot gases flowing from across the hallway are having an impact and burning off the paint and the paper from the gypboard here. Similarly on the ceiling, we've got some uniform thermal damage. But then as we hit this wall and come to around the window, we could see that we've got other damage that appears to be emanating from here. And that's in part because the fresh air coming in here is supporting the bed burning. And then we have the flames actually coming up and trying to come out the window, where down here low, we've got fresh air coming in. We've had the pillows for the bed here and the comforter. And so the bed's burned away. The bed was located right here. And so this is evidence of the bed burning, the heat coming up and around and causing this damage, which appears to be somewhat disconnected from the rest of the damage. But part of the reason is because in the hallway and this side of the room basically did not have a source of fresh air. The only source of fresh air was coming from this window, which caused this damage pattern here. So in summary, given that it's a ventilation fire, a ventilation limited fire, as we increased the ventilation, that resulted in additional burn time, additional fire growth, higher heat release rates, and increased fire damage. Fire patterns within the room of origin led to the area of origin when you consider the impact of ventilation and the positioning of the vents. Fire patterns generated pre-flashover persisted post-flashover, provided the intake ventilation points were remote. So right now we're trying to better define what does remote mean. Certainly if we had an area of ignition in a corner between 2 walls that had a window, say 4 feet or 1.2 meters off of the corner, and both windows were sources of ventilation, that would be enough ventilation to clean burn that area and basically wipe out any evidence of the pre-flashover fire. It appears that if the vent gets maybe 2 meters, 2 to 3 meters away from that area of origin, that that pre-flashover pattern will persist post-flashover. And when we're talking post-flashover, we're looking at 5 to 6 minutes post-flashover at least. And the location of the ventilation relative to the origin of the fire could also change the location and the extent of the fire damage. This was seen most graphically in the 2-story cases where we were burning the 2-story colonial house and adding additional ventilation at the upstairs level while the area of origin was downstairs. And you could see how the amount of damage throughout the house changed pretty dramatically as the ventilation upstairs exceeded the intake ventilation downstairs. So you can find all the videos from every one of these experiments, the ranch house experiments or the colonial experiments, as well as interactive floor plans that will show you the data from all of these on our fire investigation portal. And this is the address for that. We also have some other data shown there on compartment fire experiments and some exposed electrical cable experiments where we exposed a variety of different cables from, say, printer cords up through weather resistant heavy duty extension cords to post flashover fires to see what kind of damage they incurred and how long it took for them to basically short out and stop transmitting electricity. So any questions about the work that's been completed, I guess, and then we can move on to things that we're working on.
If there's any questions, just write them in the chat box. I'll give it a minute.
And this could be questions just about the program that you took online in general, not just what was presented
I've got
here.
a question. How many people got the first exercise right? Did anyone, the first exercise on that program with the heater next to the lounge chair, next to the staircase, has anyone got that right?
Most of the people, when we did it as part of a training exercise just outside of Chicago. And I would say that all of the active investigators really liked the heater. And in some cases, when we went back into that building after we did the classroom discussion to tell them it was not that heater, they still wanted to argue with me, even though they had their hand on the crumpled newspaper ashes where we started the fire.
Yeah. Well,
it took some convincing, but I think the understanding is there. So that case gets used in a lot of different classes, like at the U.S. Fire Academy and other places, to try to provide some enlightenment. Like, hey, you think about this, think where the air is coming from. That's really important.
I've got a comment here. The heat release rates in the first plot show that the potential for the fire spread to secondary combustible materials is much greater than with traditional materials. Yeah, okay, that's a comment.
True. Yeah.
And then we've got another question. Were there similar results seen between Governor's Island and these burns for the ventilation experiments? I'm not sure. What
Yes.
Yeah.
Yes. So Governor's Island, we had a number of cases where we started a fire in a room interior. Governor's Island were townhouses. And so typically they had a room on the front side of the building and on the back side of the building. And in many cases, there was a room in between. So if you imagine the kitchen was on the front, and then there was a dining room in the middle, and then the living room was on the rear. So in many cases, we'd start the fire in the dining room. And depending on if we had the living room window open or the kitchen window open, or what order they failed, the fire would move in that direction. So that we had fire investigators come out to look at that as well, because they would, they had a kitchen that was completely burned out. They had a fire in the dining room, which was not completely burned out, was not flashed over. And so the question was the dining room the victim of the flashover in the kitchen, or was the dining room where the fire started, ran out of oxygen, and then moved into the kitchen, which actually was the case. And so that was challenging some of the investigators at the time. And again, part of it is how we're starting the fires. So we use an electric match to start the fires, so we could start the fires remotely.
Yep.
And that, if we tell them what they're looking for, then, and they dig hard enough, then they can find the electric match or the remains of the electric match. So then, okay, yeah, that's where the fire started. Okay.
Yeah.
Where again, if we were using a flammable liquid to ignite or something like that, depending on if they've got a dog or what the scenario is, it might be a little more challenging. We do have dogs come through our fire scenes, but so far that's only been as training. So their trainers will dope the scene after we're all done. They like the fact that it gives the dog a fire background to work in, where everything's charred and off gassing and smelly, as opposed to them just, putting a denatured gasoline sample in their office somewhere so they can eat lunch,
Yeah. I've got another question. Fiberglass skylights in factories, destruction helps or not with fire spread? I'm assuming, so when the fiberglass, do you have fiberglass skylights in
Yes.
the US? Yeah. So obviously when they get destroyed, does it help with the fire spread?
Absolutely. So we've got a program on strip malls, training program on strip malls. And in one of those, you'll see a strip mall that we're burning, and we do some vertical ventilation with it. And you'll see flow reversal at the front door. The front door of the strip mall, like the entry to the shop, is the only thing that's open. And so initially smoke is pouring out of it, but then as we start to open the vertical vents, the flow reverses at the front door. The fire service incorrectly thinks in many cases that they're getting lift, but the volume of a strip mall is, when it's full of smoke, cutting a hole that is a meter by a meter or so is doing nothing other than improving the ventilation to make the heat release rate increase. So what's actually happening is now the door is a full intake, more air's going in, the fire gets bigger inside, the damage spread, there's more damage inside, and it's going to result in a structural collapse sooner if it's allowed to continue to burn that way. So it definitely changes the fire development inside and the resulting damage, and therefore the fire patterns.
Yeah.
So if folks get a chance to look at that, I would encourage them. That's a really good video we have. As we start to open up the roof, you see the temperature increasing. And then just after that, we show you a FDS simulation to show how the fire's growing, and there's recirculation in one end and fresh air feeding the fire on the other end.
Sorry, can you just remind everyone where that video is? Where was that video?
that would live in our, so where everybody went to the Fire Safety Academy to take the training for the impact of ventilation course, there's a course on strip malls. Yeah. And that video is in the strip mall course.
Okay.
I could probably pull that video out and send a link to you if you want to share with your members.
Yeah. I've got another question from Bob. Does UL conduct any testing on motor vehicles? Probably not.
We haven't yet, but clearly electric vehicles are in our sights. We've been collecting runoff water from vehicle fires. With the wildland urban interface fires in the United States, and so many vehicles getting burned up and so many homes getting destroyed, they're noticing some groundwater problems. And so we're trying to make some measurements to sort of come up with some source term numbers for what kind of contamination you might expect to come out of a house, come out of a regular vehicle, and then come out of a electric vehicle, battery powered vehicle.
What are your thoughts on lithium batteries in regards to vehicles? Do you think we're going to get a lot of fires eventually, and then people are going to think that this may have been a bad idea?
Well, it's kind of interesting. So in India right now, uh, they're really trying to get rid of gasoline powered scooters and replace them with electric powered scooters. And they're having so many fires with the scooters just on the street that I think the population of India is like, I think I'll hang on to my gas powered scooter for a little while longer.
Yeah.
So this is a challenge. In New York City, scooter fires, e-bike or scooter fires, they're having almost one a day now. And they've had a number of fatal ones. And it's one thing if, somebody's charging their e-bike or e-scooter and they, live on the ground floor and they can exit easily. And when the fire department comes, they can cool the fire with a hose and then throw the thing outside. So if it reignites, it's reigniting outside and they can deal with it. It's another problem when that e-scooter's on the 40th floor of a building and people are charging it typically right in front of their only exit from their apartment.
Mm.
And then they can't get out, they're trapped. Then the fire service has to deal with it, bringing it out of the building. They don't want it to reignite in the elevator or in the lift or the stairs. So now their policy is the hazmat teams come on every e-bike fire.
Yeah.
So the hazmat crews are getting a lot more work than they ever had before.
All right, I've got another question. Was any of the data put into a FDS program prior to the experiments to see what results might be expected compared to actual results?
So what we did with these is FDS was used we did some gas burner fires in these before we put furniture in it. And so FDS was used so we could decide what openings we wanted to make or not make. And so those gas burner fires are part of our repository that you can access through our portal. And they're also part of the repository at NIST for the validation studies for FDS.
Okay.
So we did that for the Colonial and the Ranch. In the studies that we'll talk about next that we're currently doing, we are running FDS on the HVAC systems beforehand to help us place position our instruments.
All right, cool. I think that's it for the questions for now. So I think you can move on to the next bit.
Cool. So some other work that we're doing is looking at how your job impacts your health and what kind of protection you should wear on the fire scene. And so if you look at these, if you scan these QR codes with your phone, you can get easy access. These journal articles live for free on our webpage, but the QR code will take you directly to this article. And the other QR code on the right will take you to a video that tells you a little bit about the project. And I'll give you a brief background here. We ran a series of tests in these structures that we have built. They're about 150 square meters, as you can see, 4 bedrooms, 2 bath, nice open kitchen, living room, beautiful counter space, move-in condition, no problem. It's they're ready to go. These are some of the most realistic homes that we've ever built for testing. They're insulated, the attics are insulated, and they have functional HVAC systems. So again, this is the kind of fuel load that we have. We're using the bright yellow curtains to help us see from the outside when they drop, when they're there or when they're not, that kind of thing. You sort of see a 3D view of the test arrangement that we were using when we were testing post-fire. So what we would do is we'd run a fire either in a bedroom or in the kitchen or in the living room. And then we would we would make tests as the firefighters were leaving. Then we would wait 24 hours. We'd button it up, wait 24 hours and make measurements again. And then 3 days after the fire, and then 5 days after the fire. As you know, many times the fire investigator doesn't come until several days later. So we were trying to get an idea of what hazard remained over that time period. So the furnishings, again, we had a lot of polyurethane foams, polyester batting, medium density fiberboard, the MDF, with different kinds of laminates on it, vinyl laminates, polystyrene laminates. Carpeting was made out of basically recycled water bottles. Then we had polyurethane foam underneath. In the kitchens, we collected a lot of different plastics, latex paint on the walls, window frames are vinyl. We had refrigerators in each one, so a variety of plastics plus the refrigerant. So we had basically a regular house. That gives you an indication of one of the bedroom fires and the post view. So the upper image on the right here, this is the room of origin, and then this is the room adjacent to it that is part of a firefighting action. This door was open and this window was open, so it pulled heat into this room, and you could see that it pyrolyzed all the bedding down to the foam cushion off of that sofa, but it couldn't get enough oxygen to ignite. And then this is an example of one of the kitchen fires that spread into the living room. And so then you see post-fire the kitchen and the living room. So we're measuring for aldehydes, we're measuring for fibrous, basically particulates there, hydrogen cyanide, hydrogen sulfide, metals, VOCs. We had a real-time particulate measurement device, the dust tracker, and we're also looking for asphyxiant gases with a real-time chemical cell meter to compare to the things that we send off to the lab. So we're comparing against these different definitions that have been identified by the International Association of Arson Investigators. Hot scene A, so the fire's just been extinguished and overhaul has commenced. Hot scene B, where the fire scene's been fully extinguished and overhauled for less than a few hours. And then the warm scene between 2 hours and 3 days, and the cold scene more than 3 days. So our take-home messages were that there were elevated levels of airborne particulate always. So unless the scene is really wet, you know, something that would be keeping dust down or particulate down, you should wear respiratory protection from particulates. Anytime we dug or moved something, the particulates would go up significantly. And in many cases, these are particulates that you can't see. So the idea of kind of like shining your flashlight in there and saying, oh, I don't see any particulates in the air, we must be good to go. The challenge is that the particulates that will penetrate your lungs the deepest, 10 micron and below, we can't see them. So just to be on the safe side, you'd want to wear some respiratory protection post-fire. And then in terms of the gases didn't persist very long. Formaldehyde, though, was there at least through the warm scene. And again, formaldehyde is not something that's usually detected as part of a 6 gas meter suite. Formaldehyde usually isn't one of those detectors. So the gases didn't seem to be that much of a problem if you're 1 or 2 days out. That seemed to clear. Now, one of the complaints we got about the test was that our fire scenes were way too clean. There wasn't enough piled paper, there wasn't enough books, there wasn't enough debris all over the place. And so one of the things we're going to do next is run some experiments where we should end up with a lot of drop down, maybe half a meter of debris on the floor, that kind of thing. The question is, does that trap the gases or not? So that's what we're looking for there. Something we're doing right now, we ran a couple of fires last week, and we're hoping to run some more next week, as we've got a couple of folks we're referring to as our industrial hygiene team, because it contains a certified industrial hygienist, and they're responding to fires with the LA County Fire Department. So that's, we're going to get some ground truth out of that. Pardon me. This is a series of tests that's ongoing now. We're getting ready to start up again. We took a break for the winter. We're looking at the impact of HVAC systems on how it spreads smoke to parts of the building that are not involved in fire, what kind of damage we see, that sort of thing. Again, we're using these same houses. We have two of them that are similar. One of them has air supplies at the ceiling. One has air supplies at the floor. This is our typical instrumentation that we're doing. Thermocouple arrays in all the rooms and in the hallways. Gas concentrations at multiple levels. On the interior walls. I lost my cursor here, sorry. On the interior walls adjacent to the closets or the bathrooms, we've got heat flux gauges at 3 different levels on the wall, oxygen concentrations at 3 different levels on the wall. In front of the windows, we have oxygen concentrations at the windowsill and near the air supply vent, whether it's at the floor or at the ceiling. Heat fluxes, bidirectional probes to look at flows down the hallway or out of the doors. This is a view of the ceiling supplied HVAC system. The flow coming out of the system should be able to support a small flaming fire on the order of 50 to 100 kilowatts. We're keeping our fuel load pretty simple. We're lighting a Sofon fire. We've got a wood target box there that you see that's instrumented with TCs and heat flux gauges on the front and on the top. Here's our oxygen probes, our pressure probes, and our heat flux gauges on the wall opposite the area of origin. Some of the damage post-fire. Some things that we see remote from the fire room. So here we can see that the return was full of hot air. And as a result, that heated the gypsum board so that the gypsum board that is part of the return bay was heated. So the soot didn't condense on it as much. So as a result, we've got this cleaner area and heavier soot on either side. We could see a similar thing here on the returns in the hallway. Here we see that we're blowing heated air out of the vent, the floor vent, that's impacting the wall. And where it impacts the wall, it won't let the soot condense. We don't have a big enough temperature differential. We're going to watch a video real quick because what you're going to see here is kind of interesting. The HVAC system's running. It's going to allow the fire to continue to burn, even though the fire is very much the room is oxygen depleted in general. So the fire can only burn in a limited area. It's going to allow it to burn. That burn time is going to heat the window frame and cause leakage in the vinyl window frame, which will start to serve as an exhaust. The door to the room is closed, and so it's going to start to pull air from under the door, and we're going to get airflows under the door on the order of 10 miles an hour at certain points of time. And as the window continues to fail, an interesting thing happens. Early on, the fire doesn't move toward the window. You're going to see it move toward the door because that's the source of oxygen. Then once the door burns away and we get some better mixing in the room, then we'll see the flames and the heat return back to the window. But it's kind of interesting initially as the window starts to fail and let the hot gas out, there's enough fresh air pulled in under the door that the fire actually moves toward the door. So here we've got, we're going to start our fire on this sofa. The door is on this side. The windows are on this side. The door's closed. this view down the hallway, our fire room is on this side of the hallway. And you'll see some heat signatures coming out, initially leaking around the door. And then you'll be able to see when the door catches fire and fails. So we're starting the fire remote from the window so we don't fail the window right away. It's going to be interesting here to watch the smoke start to leak out in the hallway and slowly spread. Down the hall and then into the living room and kitchen area. So about 3.5 minutes in, the fire's already darkened down. Look at the pressure in the hallway IR view. Look at the pressure pushing under the door. And then you see the pressure fade. You see it puff. The fire's really struggling to breathe now. It's in that oxygen depleted decay phase. And so it would appear that the fire's basically shut itself down. However, the HVAC system's continuing to run. And if you look in the video view of room 3 in the lower left corner there, you'll see that we still have flaming combustion going on in the room of origin. Then as you look at the exterior views, you'll start to see leakage. That you'll notice when the fire is growing, we get a push of smoke from under the door in the hallway. And then when the fire is going into decay, we kind of lose it until the point that we've got enough exhaust coming from the window or leaking around the windows that we're then pulling our air supply in from the hallway. So the window's starting to open up a little more. We're getting some failure. And as the window opens up and fails, what we're going to see is the fire is going to move toward the left of the screen, which is toward the door, as opposed to toward the right of the screen, which is toward the window. See the flame front moving toward the door? Now, as we watch the hallway IR view, we're going to see that the doorway is going to catch fire. The door itself is going to catch fire. The window has cleared itself. And now basically we've got flames throughout the room. And then once the doorway burns away, basically all the burning at that side of the room will stop. And so we can see our temperature curve where the fire built up. It went into oxygen depleted decay. We got some more burning based on the leakage starting at the window and the fresh air circulating from the HVAC system supporting it. Then the window really begins to fall out, and that increases the burning even more until we basically get to a flashover type condition. The oxygen concentrations on the wall opposite the sofa toward the ceiling, mid-height, and toward the floor, we see that they drop below 15% pretty quickly. The blue line being the oxygen. But we notice that at 0.1 meter above the floor, or 4 inches above the floor, we're maintaining some oxygen down there, right on the threshold here. But this is allowing the fire to continue to burn, and that air is coming in through the vent. So even though we're recirculating some oxygen depleted gases, it's able to pull enough fresh air from other parts of the house to maintain about a 20% or 19% oxygen concentration to allow that fire to continue to burn. Pressures that we have built up in the space, you can see that we're getting up to 25, 30 Pascal there early on. We have another spike as the fire is sort of breathing, if you will. And then once we start to fail the window, the pressure drops. And once the window's out, this room is actually at negative pressure with its high rate of exhaust. The velocity's out the window. I need to re-edit this one so we clip off some of this, but you can see that we've got velocities getting close to 5 to 10 meters per second. So the velocities are moving out of the window pretty quick. Our target box that we have in there, we can tell when it starts to burn. And so we're making measurements as to how much wood is burned away in that period of time. We've also got our heat flux measurements on the wall. So again, this is a work in progress. So far, we've had no localized burning around the HVAC vents, no localized patterns, which is kind of surprising to me, which is one reason why I had the wood box next to the vent so that we'd have fuel right there. The closed HVAC system without a filter or with a poor quality filter enables continued burning for an extended period of time. With a high quality filter, I guess they have these MERV ratings on the filters now. So if you have like a MERV 8, that filter will clog with soot and reduce the flow. The single sofa fires with a closed door small room self-extinguished if no window was available to fail. Sofa fires with the door open continue to flash over with or without HVAC. So far, we haven't seen any significant difference between the ceiling supply or the floor supply in either fire behavior or fire pattern. And the soot condensation patterns remote from the fire, you may be able to use to tell if the HVAC system was operating at the time of the fire or not. Also, the clogging of the air filter may indicate whether the HVAC system was operating at the time of the fire. Some other work we're doing, again, to sort of support modeling and some back of the envelope calculations we're taking another look at flame height calculations, time to flashover calculations, CFAST and FDS with a series of free burns and compartment burns, over 100 in all. And the reports are out with the data, and some of the analysis is continuing. And there's actually an international group working on it, which includes representatives, I believe, from the University of Melbourne that are a part of the team with Ghent and the University of Maryland to examine the data from this. We're also working on developing a contemporary database of materials. Most of the material properties data that we're using for fire modeling input, a lot of it's from the 1970s and the 1980s. And things like even gypsum board have changed in their makeup and in their density in the past 10 years. Polyurethane foams have changed somewhat since Hurricane Katrina, at least in the United States, they've changed. So we're trying to look at some of these. And then there's other materials that are being used for carpeting now that weren't used for carpeting in the 1970s, like the recycled water bottles and things like that. So again, this will be, we're hoping to post our first set of materials, about 60 or 70 of them online in October, and then continue to grow it from there. We're also doing some work on backdraft and smoke explosions. Again, small scale at this point, but moving forward. So again, you can get there. We have a lot of information available at training.fsri.org, our Fire Safety Academy, where you took the class, and our webpage. If you check in on that and just sort of search under fire investigation, it should keep you up to the research we're doing related to fire investigation, whether for fire investigators or if we're doing near miss analysis or line of duty death investigations, things like that. It would pop up, and that's fsri.org.
Excellent. We do have a couple of questions. I've got a question. It's saying are the windows single or double glazed? Well, I guess to add on to that, is there any difference between single and double glazed windows if you're doing testing on that?
Yes. So these were double glazed windows. The single pane windows don't take as much energy to automatically vent and fail. The double pane windows take a tremendous amount of energy for the fire to vent. Glass, as we know, is a great insulator. And with the inert gas that they typically fill in between, again, another good insulator. So it takes a tremendous amount of energy to actually fail the glass as opposed to failing the window frame.
So those second experiments, they were all double glazed windows, were they?
Yes.
Yeah, okay. You got a good budget because they're expensive. You got another one. Was the ceiling in the floor, or was was that a ceiling or floor vent? I think it was a floor vent.
Yes.
Yeah, floor vents. Any difference between ceiling vents?
We haven't seen it yet. We've got another series of about 10 experiments to run this year, starting the end of June, going in through July, and then a few in October, and trying to see if we could see some difference. Another thing we're going to do is we're on a couple of them, we're going to make some leakage around the air supply, because our air supplies are well insulated and tight. And as we were talking the other day, they're made out of solid steel. They're not the coil wires or anything like that. And some people are seeing patterns right by the air vent. And I think that's due to leakage, actual outside leakage. So like if I drill a hole for an instrumentation line and I don't plug it appropriately, we'll see a nice burn pattern right there from air being drawn in from the outside.
Yeah, I'm assuming that the ceiling fans would just get overpressurized by the pressure in the room, even if it's trying to pump air out. I'm assuming they'll be forcing against each other.
We see some reduction in flow, but we don't see it stop.
Yeah, okay.
And that's true for both the if we have the door closed to the fire room, that's true for both types of systems, because the pressure builds up.
I've got another question.
It doesn't stop. It just reduces the flow.
Just slows it down. I've got another question. It says including vinyl flames. So I'm assuming, does it make a difference if the window frames are vinyl, metal, or aluminium?
So these are vinyl frames. Aluminum frames, of course, will, if impacted by fire, would melt as well. The stronger frames, if we have wood frames that are then vinyl or aluminum covered, those are the strongest frames. And again, that takes even a longer period of time or more energy to fail those.
Yep. Okay. I've got another question, a little off scope, but have you done any testing on heat detectors as opposed to smoke detectors for safety within residential properties or occupancy alarms to fires?
No, everything that we've done is with smoke detectors. We're looking forward to doing some real world testing with the new standard detectors, the neural network detectors that are coming out. But we're on hold. We're waiting for those. They're not here yet.
Yeah. If there's any other questions, feel free to ask. Otherwise, we might be wrapping it up in a minute. I just want to make everyone aware that Dan has gotten up at 4 a.m. to provide us with his presentation. So make sure you thank him in the chat box, please. No, I really appreciate it, Dan. You doing this for us and accommodating for our time. That's really nice of you. Hopefully we can get you out here sooner rather than later to do attend one of our conferences and do some presentations for us. So yeah, we'll see how that goes in the near future, but good luck with all your research. It's very interesting research, especially for fire investigators, and you're doing a lot of good stuff for everyone. So really appreciate it.
Thank you very much.
No worries. I think that's it, guys. Everyone have a great day. Great evening. You're obviously getting a lot of thanks in the chat that you can have a look at, and yeah, appreciate it. Thanks, Dan.
Thank you.
Just another reminder to everyone that the conference is coming up in November, so look out for the messages coming out for that. And there's also the vehicle training course. Forbesy, do you have something to say? You got to take yourself off mute. I'll take yourself off mute, Forbesy.
It's not getting that.
He's not on mute. He's off mute though.
How about now?
Yeah, I can hear you now.
Oh, I hit the wrong button. Yes, AGM in August. We having a social night and AGM. And if you would like to join our committee, please let me know. Yes, the AAFI conference, please support it. And then certainly we've got the IAAI Motor Vehicle Fire Investigation course being conducted in Brisbane from Monday the 31st of October to Wednesday the 2nd of October, and then from the Gold Coast, down the Gold Coast for the AAFI conference from the Wednesday evening through to Thursday and Friday, 2nd, 3rd and 4th of November. Please support it. More information will come out via our website and email blasts. Thank you for turning up tonight. Thanks to Dan, unbelievable effort, a real person in this fire investigation industry in the world who has got the experience around research and fire research they're doing. UL is just doing an amazing job, and we are all on their backs, sort of learning from them and learning what they can do and how they're doing it. So thank you very much, Dan. Thank you all. We'll see you next time. Thank you, Mark, for stepping up and organising this one as well. Very well done, Mark. Thank you.
Okay, I'm killing
Dan, and bye everybody.